Welcome to the next episode of Logic Made Lucid. Today we're going to go over quantifiers in predicate logic. This video already assumes a basic understanding of predicate logic, the use of symbols, the use of operators, and the rules of inference, and so forth. So a quantifier signals whether a statement refers to all things or the existence of something, or at least one thing. It's kind of equivalent to the word some or something, right? It clarifies whether a quantitative statement is universal, i.e. it refers to all of a category, or particular, it refers to the presence of something, that there is something. So variables are used to label what is being quantified. So we typically would use x, y, or z. Those constants are typically designated as variables, and all the other letters of the alphabet, in their lowercase form, of course, are constants. So as an example in predicate logic, we could have a predicate P, meaning is a penguin, or the predicate B, meaning is a bird. So we have for all x, px implies bx. We're saying if anything is a penguin, then it's a bird. Or similarly, if we have there exists a y such that py and by, we're saying there is something that is a penguin and is a bird. All right, using a couple of other operators, we could say let m mean the predicate is moving and s mean the predicate is stationary. We could say for all z, mz or sz. So everything is moving or everything is stationary. And similarly, we could say there exists an x such that not mx. In other words, there is something that is not moving. And notice here I've tried to use the quantifiers with all four of the logical operators that we have been studying: implies, and, or, and negation. All right, so the importance of quantifiers in predicate logic. They are valuable because they define the quantitative property of a variable. And this is needed because if we think of the statement mz or sz, right? So something is moving, z is moving, or z is stationary. Well, it's unclear whether z refers to everything or something, right? So it's a variable, meaning that there's a lot that we could plug into it. So are we referring to everything or just something? So the quantifier, universal or particular quantifier, is needed. Are we referring to all of something or just an example of something? So here we have everything is moving or everything is stationary. And here we have there exists something that's moving or stationary. Okay, there's an important difference logically in those. So one of the things that we can do with quantifiers in order to use them deductively is to instantiate them. So instantiation is similar to saying for instance or for example, right? So what it does is it preserves the quantifier's logical meaning, but it removes the quantifier so that we can enable further deduction. When we instantiate, each corresponding variable gets replaced with some sort of instantial letter. Typically, it's kind of arbitrary which instantial letter you might use, although there are some important rules that we need to follow, and we'll discuss those pretty soon. Universal instantiation, so if we're talking about all of something, there are two forms that can take. If we say for all x, px implies bx, well, we could say on the left, we could say that means px implies bx, or we can say pa implies ba. In the left case, we're talking about a variable. We're replacing the universal statement with a variable-based statement. So we go from for all x, px implies bx, to something that would be read like if x is p, then x is b. Right? Now on the right, what we do is we add a constant. Right? Now if we think about this in terms of the way we might ordinarily express something, we might say all penguins are birds. Well, another way of putting that could be what's said at the top, and then on the left we could say penguins are birds, right? Or if something's a penguin, then something's a bird. That would be on the left. On the right, we're saying something like all penguins are birds, but then we're saying this penguin is this is a penguin, and so this is a bird. So this a, and so a could be Albert or whatever, is a penguin, and so Albert is a bird. It's Oh yeah, it's important to also recognize that what we're doing here is we are using implications, right? Now there are two forms, you'll remember, there are two kinds of inference. There's implication and there's replacement. Implications need to apply to the entire line. So this is only applicable if the quantifier refers to the entire line. Otherwise, you have to use some other method. If the quantifier applies to the entire line, then you can take the entire line and remove the quantifier by replacing it with an instantiating letter. So they apply the entire line. Now, if there were rules of replacement, if they were that kind of inference, then we would be able to replace a segment of the line, of course. And this is what we had talked about before. All right, so that's universal instantiation. With existential instantiation, you're taking an existential statement, an existential quantifier, and you're going to replace the variable with a constant, right? So the top line, we can think of that as saying there exists something that is a penguin and is a bird, right? You can see this on the left. There exists a y such that y is p and y is b, right? Y is a penguin and y is a bird. So what we could do is we can use existential instantiation. We can instantiate that by saying an arbitrary name, Nigel, say. Nigel is a penguin and Nigel is a bird, right? That's taking, for instance, let's say there's a penguin called Nigel who will also be a penguin called, I'm sorry, a bird called Nigel. So what we have is n is p and n is b, right? So we have an arbitrary constant n and so forth, right? All right, if there is another line with an existential qualifier, and this is probably one of the most important rules in an area where people sometimes get tripped up in predicate logic using quantifiers. If there's another line with an existential quantifier, so we've got on the left, we have exactly what we had on the previous screen. There exists a y such that py and by, that it's a penguin and it's a bird. And then by instantiation, we could say Nigel is a penguin and Nigel is a bird on the left. So let's say on the right, we have there exists something such that it is moving or it is stationary, using the same predicates as before, with m meaning is moving and s meaning is stationary, right? Well, we may be tempted to use the same letter, right? If we accidentally use the same letter or if we intend to use the same letter. This is actually problematic because now this new line and this new example of instantiation is by accident or by purpose, but not by any kind of valid logical deduction using the same constant as the previous line had done. But we cannot do that because we cannot assume that this second line, this line on the right, refers to the same thing as the line on the left. So we can't use the same constant as the previous instantiation from an existence. We have to use a different one. So the rule is, when instantiating existentially, it's crucial to select a different constant than any that appear in earlier lines, so that one is not confused with the other. So let me give you an example of how why this can be erroneous. Another more specific example. So let's say there exists, again, something that is both a penguin and a bird, right? There is something that is a penguin and a bird. Well, let's say we also have an existential statement where we say there is something that is both a canary and a bird, right? So we've got there's something that is a penguin and a bird, and there's something that's a canary and a bird, right? Both of these are fine. They can exist together as logical statements. All right, well then let's say we instantiate the first line. We take the first line and we say Nigel is a penguin and Nigel is a bird. We've arbitrarily chosen the name Nigel to name a specific penguin. Right? And we know that we can do this because if there exists something that's a penguin and a bird, well, we can label that. We can name it. This penguin, which is also a bird, let's call it Nigel. Right? Okay, now let's say we take the second line and we instantiate it. We say Nigel is a canary and Nigel is a bird. Right? Now we're going to run into a problem because we have violated that rule that we described in the previous slide. We've taken a second existential instantiation but we've used the same constant as in a previous line, but we cannot do that. Now watch what happens. So through simplification and commutation, we end up with Pn and Cn. Basically, we're just kind of switching things around a little bit, but with all these additions, we have Nigel is a penguin and Nigel is a canary, right? Because you can see this in the previous lines. Notice we've got Pn, we also have CN, right? Nigel is a penguin and Nigel is a canary. Well, that means that by existential generalization, which we'll talk about soon, that means that there exists something that's both a penguin and a canary. But we know that's not true. That's a mistake, right? So we've accidentally created something that is both a penguin and a canary through this error in our logical steps. So the error, of course, exists in line 4, right? We cannot move from line 2 to line 4. We cannot instantiate by using the same letter as a previous one. So this is invalid because it duplicates a constant from an earlier line. So we see an example of how existential instantiation can trip us up if we accidentally use the same constant as appeared in the previous line. Now, just as what we just saw, you can generalize also. So there's instantiation where you're finding an instance of something, but then there's also generalization. Generalization, it restores or adds a quantifier. And in this case, we're talking about existential generalization. So we're restoring the existential quantifier here. What it does is it converts a variable it converts a constant into a variable by recognizing that at least one thing with those properties exists. Right? So if we say Harry is a penguin, well, then we know that there exists at least one thing that is a penguin, right? So that something is a penguin. So let's say we have Nigel is a penguin and Nigel is a bird. Well, we know that there exists something that's a penguin and a bird, right? So we can generalize existentially from a statement that involves constants. All right, now there's another kind of generalization, universal generalization, and this is what adds the quantifier all for all x to a statement with a variable. So let's say we have, if something is a penguin, then it's a bird. Well, by universal generalization, we can say that for all penguins, or for all things, if it's a penguin, then it's a bird. If anything is a penguin, then it's a bird. So these are logically equivalent statements that we can make. All right. I'm sorry, logically equivalent, not exactly, but one follows from the other by implication. Okay. All right. Note, you cannot go from a constant to a universal, right? That would be like saying, let's see if I did this. If I were to do this, so let's say I've got something involving constants, PC or NC, right? We could say this charge C, is either positive or negative, right? We could say that. So if we're talking about electronics, this charge is either positive or negative. Well, I can't universalize that. I can't make a universal generalization based on that. And I can't say everything is either positive or negative from that. Notice what I've done here. So notice the error. I've taken that constant C and then I've universalized it into a variable x, and I've said for all. I cannot do that. Now I could use existential generalization, and I could say that there exists at least one thing that is either positive or negative, but I can't say that all things are therefore positive or negative. Okay, so that's an important limit to universal generalization. I cannot take a statement with a constant and then generalize that universally. I cannot say that all things meet those criteria. Okay, so in summary, a way to kind of depict this, or a way to kind of have all of these rules kind of all together, right? We've got your universal quantifier in the upper left. All things are real. Let's say R is the predicate is real. So all things are real in the upper left. That's a universal quantifier. And in the upper right, we've got an existential quantifier. We've got there exists something that is real. Something is real, right? In the lower left, we have things are real, Rx, right? This means that anything I plug in for x, it's going to be real. And then in the lower right, I've got this thing is real, some arbitrary constant n, and that is real. This thing n is real. Okay, so as a reminder of what we can do by implication, where we can go, what directions we can move with these, we can move from a universal quantifier into a statement with a variable, right? As long as we take all of the x's that are in the universal quantifier statement and we convert them into some kind of variable. So that's a universal instantiation, right? Now we can also use universal instantiation and get a constant, right? So we could do either one with universal instantiation. And this is like saying, if I say all things are real, well then this thing n, this arbitrary thing n, is going to be real. Because I've already said all things are real, right? It's like saying if all things are made of energy, then my computer is made of an energy, or I am made of energy, right? It follows logically. So we can do that with universal instantiation. Now, from this statement Rx, right, we can go in the other direction. We can universalize Rx, right? If I say things are real, then I can universalize that to say all things are real. Because I've said simply things are real. Well, then I'm implying that all things are real. So that is called universal generalization. Right? Now, when we go over to the right side, we can go from an existential quantifier to a statement with a constant, saying this thing is real. But we need to remember that when we're using existential instantiation, the constant must not duplicate any previous constant in the proof. You'll remember how we just explained that. Okay, and then finally, the other step we can make, the other logical step we can make, is to say that if Rn, then there exists something that is R, right? We can use existential generalization there. All right, so let me give an example of a deductive proof that uses a couple of these implications. All right, so let's say we have this statement: all humans with cowpox don't die of smallpox, right? So we've got for all x, hx and cx implies not sx, right? So h means is a human, c means has cowpox, and s means dies of smallpox, right? So that's what S means, dies of smallpox. So for all x, if hx and cx, then not sx. Okay, that's this universal quantifier applied to a particular statement. Right? Okay, now let's say we also have some more information. Let's say Andrew dies of smallpox. So we've got SA. And Andrew is a human, right? So HA, right? So Andrew dies of smallpox and he is human. So notice the constant A refers to specifically Andrew, right here. All right, now let's say we want to show, based on this information, we want to show that there exists something that does not have cowpox. Right, do we see this? With the green, this is what we want to show. We want to take the information that we have in statements 1, 2, and 3, and then we want to show from that, we want to deduce that there exists something that does not have cowpox, right? There is something without cowpox. That's what we want to show. So we can take the first two statements: all humans with cowpox don't die of smallpox, and Andrew dies of smallpox and he is human. Take those and then we can show that there is something in the universe without cowpox. All right. So one step we can take is we can use universal instantiation. We can take this first statement and then we can convert that into a statement that involves a constant. Now we can, with universal instantiation, we can use the same constant as appeared earlier in the proof. We can do that because we've made a universal statement which applies to everything in the universe, right? For all x, no matter what I plug in for x, if hx and cx, then not sx, right? So I can do this with universal instantiation. Now remember, I cannot do it with existential instantiation. All right, so there I am. So now I've got Andrew is a human, or if Andrew is a human and Andrew has cowpox, then Andrew does not die of smallpox, basically. This is what this statement 4 says. Okay. All right, well, what I can use next is a rule of implication, an implication here, rule of inference, which is an implication called double negation. I could take statement 2, so notice statement 2 is Andrew dies of smallpox, and I can say not Andrew dies of smallpox. Now this is valuable. It's maybe a bit of a unnecessary step, because really what I intend to do here is I intend to use modus tollens with statements 4 and 5, and I'm going to show that not HA and CA. In other words, it's not the case that something is both a human, or that Andrew is both a human and that Andrew has cowpox. Right? It's not the case that Andrew is a human and Andrew has cowpox. All right, and I use that by modus tollens from statements 4 and 5. Right? All right, so that's modus tollens. Here's a reminder of what modus tollens is. P implies Q, not Q, therefore not P. Okay? Now from there, from statement 6, I can use De Morgan's theorem, right? I've got, it's not the case that Andrew is a human and Andrew has cowpox. Well, from that, I can say either Andrew is not a human or Andrew doesn't have cowpox, right? One or the other, right? Now, they could be both, but we could say Andrew is not human or Andrew does not have cowpox. Well, that's De Morgan's theorem. As a reminder, this is one application of De Morgan's theorem. Now, De Morgan's theorem is a rule of replacement, right? Which means we can take a segment of a line. Now, this is not necessary here because we've done this with the entire line, but you could take a small segment of a line, and if you see this structure, then you can replace it with the latter structure. It's a rule of replacement. Okay, well, from there, we can say, well, not HA. Now, what I'm doing here is I'm taking line 3, where I say Andrew is a human, and I'm just using double negation to say Andrew is not a human. Right? And the reason why I want to use this, want to take this step, is because I want to use it with statement 7, and I want to use a disjunctive syllogism here, right? Because what I'm saying is either Andrew is not a human or Andrew is not doesn't have cowpox. Well, Andrew's not a human, right? Andrew is a human, and so the remaining element of the disjunctive syllogism must be the case. So Andrew does not have cowpox, right? And again, with disjunctive syllogism, it's basically saying P or Q. Well, if not P, well then Q, right? If I'm going to eat an apple or an orange, but I'm not going to eat an apple, well, that means I'm going to eat an orange. All right, now from there, notice we can go from Andrew does not have cowpox. We can use existential generalization. We can say, well, because Andrew does not have cowpox, well, that means that there exists something that doesn't have cowpox, right? There exists something that doesn't have cowpox. And there we are. We have arrived at exactly where we wanted to go. We have showed that there is something that does not have cowpox. There is something in the universe that does not have cowpox. Right? So this is an example of how you can use some of these logical steps, these implications, using quantifiers in order to prove something deductively. All right. Next session, we will talk about quantifier negation. Look forward to seeing you in that one.